Lesson 94, Probability Distributions. So we've been studying probabilities so far, and one useful aspect of it is if I want to consider all the possible outcomes, say, remember when you draw a tree diagram and then you list out all the outcomes, essentially you're able to calculate the probability of each outcome happening, right? And if I account for all of the possible cases, then I can organize the information using either a table or a graph, and we call that a probability distribution. We're going to focus on discrete random variables, meaning that these variables represent quantities that are countable, that involves counting numbers like 0, 1, 2, 3, and 4 with no decimals involved. On the screen, we are summarizing the properties of probability distributions as such that first, the sum of probability when your discrete random variable uppercase x equaling to individual cases. Okay, so if I add up all the individual probabilities from 1 to n, it should equal to 1. Okay? And then any individual probabilities when x, discrete random variable x, takes on a different quantity, it's from 0 to 1. Makes sense, right? And then the probability of one event happening must equal to 1 minus the probability of that event not happening. So the notation here, x, the uppercase x is general, and then the lowercase x with subscript I indicates the ith outcome. Okay? Example 1. Two tetrahedral dice have sides labeled with 1, 2, 3, and 4 are both rolled. On a tetrahedral die, the outcome recorded is the face which lands on the ground. Let x be the sum of the down faces. A. Use a probability distribution table to organize P of x equals to x. So here, essentially what we're thinking is, what are the possible sums of these two dice? Well, starting from 1 and 1, that means the sum would be 2. And then we can step it up to sum of 3, sum of 4, 5, 6, 7, and 8, because 8 would be a 4 and a 4. And then what you can consider using would be a dice table, right? If you recall, similar to a 6 faces die, I have 1, 2, 3, 4, and 1, 2, 3, 4 here. Obviously, the largest number is 8. The smallest number is 2. And then in the diagonal, what am I going to get? 4 and 1, 5. 3 and 2, 5. 3 and 2, 5, and 5. So it kind of like helps us to determine what the probabilities are without, working out the whole thing. So how many 2s can we get? Well, we can only get 1 out of, there are 4 by 4, so 16 possible outcomes, right? How about rolling 3s? Well, we can guess that this is going to be 2 out of 16, 3 out of 16, and then when I get to the 5s, I'm on the diagonal 4 out of 16. So it makes sense, right? And we know from our experience that probability would then start to decrease. So 3 out of 16 of rolling 6, and then 2 out of 16, and then there is only 1 out of 16 sums of 8. And then here is my chart. Okay, so this is actually the table form of a probability distribution. Part B, find the mode of the distribution. Well, the mode is the most frequently occurring piece of data. So in this case, 5, right? Rolling a 5 is most frequent. So mode is when x is equal to 5. So C, find a probability distribution function. So here we have a hint. It may be useful to find two piecewise functions. Now, it makes sense because as we go up, we know that we're basically looking at 1 out of 16, then 2 out of 16, and so on. So using a piecewise function, I can say that I can relate the numerator in each probability to the value of x being always one smaller, right? So I can say that P of big X of xi, like equaling x little I, it's equal to your x value minus 1 over 16. And this works for x values between 2 up to 5. Okay? And then for x values that are greater than 5, so starting from 6, 7 up to 8, how can we determine the numerator? Because we know the denominator is still 16. Well, it looks like when x is 8, I get 1. X is 7, I get 2. So there's always this constant, right, decrease. So I can use 9 minus x. Okay. And then in the last part, we are asked to represent this distribution using a vertical line graph. So on the vertical line graph version of a probability distribution, the vertical axis represents the probability, and then the horizontal axis represents the discrete random variable. Okay, so x. And we can go from 1 over 16, 2 over 16, 3 over 16, 4 over 16, 5 out of 16. Oh, we don't really need that, but that's all right. Okay, so that's our the y-axis. And then when x is equal to 2, the height of the vertical line would be 1 out of 16. And then we just keep doing that. Okay. So 5 is the maximum. And then I start to decrease and go back to 1 out of 16 for 8. Okay. Example 2. So here we're given a function for p of x being 10 to the power of x over x factorial times e to the power of negative 1 for x equals to 0, 1, 2, and 3. So this is a discrete random variable. Find the probability of x less than or equal to 1, meaning that the cases include probability when x is equal to 0 plus the probability when x is equal to 1 only. Okay, so we're including those cases. All we have to do now is to substitute 0 first into the function and then 1 into the function. So 10 to the 0 over 0 factorial e to the negative 1 plus 10 to the 1 over 1 factorial e to the negative 1. And this gives me 1 over e plus 10 to the 1's 10, so 10 over e, which is 11 over e. Next, I want to find p of x greater than or equal to 1. What does this mean? This means that I have to include cases such as x equals to 1, x equals to 2, x equals to 3. So this is an infinite sum because my list of x values goes on forever. I can't do this. So instead, let's do the complement, which is 1 minus the unwanted case of x equals to 0. So here we already know from the last part that's 1 over e. I can write this as e minus 1 over e then. Okay? So one important aspect of a probability distribution, of course, is to find the mean, right? The expectation. So when I carry out this experiment, what am I most likely to get? Or how often, am I going to, expect to get a certain outcome? And we know that as the number of trials increases in these kind of experiments, the experimental probability, of course, will get closer and closer or converge to theoretical probability. So we call this the expectation, okay, of a distribution. So we use the symbol E of x to represent that. And it's also referred to as the mean. We use the Greek letter mu. Okay. So you'll here either find the average of the distribution or the mean of the distribution, or the expectation or the expected value of the distribution. It really refers to the same thing. And to calculate mean, we know that we have to, add up all the cases divided by the total, which turns into the sum of the value of each individual outcome multiplied by its probability. Okay? So this is the average results. And it is okay to get a decimal even though x represents discrete numbers, because this is a theoretical number. Okay? All right, so let's take a look at example 3. A robot is in the process of shooting 2 high goals. The probability of success on each shot is 0.7. Let x represent the number of points scored and complete the probability distribution table. Hence, find the expected number of the points scored. Okay, so let me erase the tut. That's poor grammar. Okay, so let's consider what's really happening here. So shooting 2 goals, so they're successful, or the robot is not successful, right? So this is the first shot. Success probability is 0.7. That means the other one's 0.3. Now the robot shoots a second goal. It gets in or it doesn't get in. Regardless of the first shot, right, there's no change to the probability of getting a second shot. So these are independent events. And I can represent everything using a tree diagram like this. If I consider the number of points scored, that means out of the 2 shots, right? What is the least number of shots that made it? Well, of course, 2 misses. Or score 1, miss 1, or score both, okay? And let's calculate the probability of each. So getting 0 goals, we're looking at S prime, so that means it's 0.3 times 0.3, which is 0.09. Getting 1 in would be 0.7, miss the second one, 0.3. The second case would be 0.3 times 0.7, so I can times this by 2, making 0.42. Okay. And then for making 2 shots, P of S and S, 0.7 times 0.7. Another way to get this number is to subtract 0.09 and 0.42 from 1, right? You can still get 0.49. Knowing that the expectation or the expected value of a distribution comes from the sum of multiplying x times P of x equals to xi, I can actually use the chart again. So I'm going to create this column or this row. Okay. Then I can easily multiply the 2 numbers on the first 2 rows. So 0 times 0.09 gives me 0. 1 times 0.42 is 0.42. 2 times 0.49, that's 0.98. Okay, so this is much clearer when I have to find the sum. Okay. Lastly, let's take a look at example 4. A discrete random variable y has probability distribution as shown. Find the exact value of k. So k is found in the probability row. Which property of probability distributions can we make use of? I think you have the right idea. that the sum of all probabilities is equal to 1. As a result, when I add k plus 2 over 5 plus 1 over 4 plus 2k, that must equal to 1. Okay, so let's add 2 over 5 plus 1 over 4. That's 8 plus 5 over 20. So here 3k must be 1 minus 13 over 20. And so k is equal to 7 over 20 divided by 3, 7 over 60. Okay. Once I know that, I can backfill. Okay, these property, this is 14 over 60. And then now I can find the expected value of y, because e of y now is equal to 2 times 7 over 60 plus 3 times 2 over 5 plus 4 times 1 over 4 plus 5 times 14 over 60. Okay, should we brave this? Why not? So 7 over 30 plus I have 6 over 5. 6 over 5 is 36 over 30 plus 1 plus I want 30. This is going to be 30, so divide that by 2, 7, so 35. What does this mean? It means I have 108 over 30. Divide by 3, I get 3, 6, 10. So this is 5 and 18. Okay, so this is equal to 3.6, which means that when I carry out this probability experiment multiple times, many times, I will expect to get y equals to 3.6 on average.